Let's start by adding up these cages. They add to 109. When we subtract off the middle 45, we get that these cells minus the middle cell is equal to 64. Now if these were all 9-8 pairs, that would add to 68. So this is at most 4. But they can't all be 9-8 pairs, because then there could no longer be a 9 and 8 in these cells. So where are the 9s and 8s in those cells? If they were in the same cage, that would mean the orange cells would add to at most 6, 7, 8, 9, 8, 9, and 8, 9, which only adds to 64. So we can no longer subtract something to get to 64. So the 9s and 8s are in different cages. Wherever the 9 is, the orange pair adds to at most 8 and 7. Wherever the 8 is, it adds to at most 9 and 7. The other ones could be at most 9 and 8. Overall, that adds up to 65. So the purple cell must be 1, and these pairs are 9-8, 9-8, 9-7, and 8-7 in some order. We'll put in 9-8-7 for now. Now, where is the 9, 8, and 7 in the blue cells? The 9 must go with the 8-7 pair, the 8 must go with the 9-7 pair, and the 7 must go with one of the 9-8 pairs. That gives us 3 9-8-7 triples, which add to 24. We can't have a 9-8-7 triple in this cage, because that would leave 1 to get to 25, and we've already used the 1. So the 9-8-7 triples must be in the other 3 cages. 9-8-7 with a 5 to get to 29, 9-8-7 with a 4 to get to 28, 9-8-7 with a 3 to get to 27, which leaves 2 and 6 here, which need 9 and 8 to get to 25. Now let's get rid of these colours, and we'll start a new colouring system. We're going to colour the 7s, 8s, and 9s in 3 different colours. We'll colour this one red, this one purple. One of these is going to be a blue. Now, can this cell be a red? And the answer is no, because this cell could no longer be a red or blue and must be purple. Now we have a red, purple, which add to the same sum. But we know this is a 9-8, and these are going to be 9-8, 9-7, and 8-7 in some order, which all add to different sums. Likewise, if this was a purple, this would be a red and would have the same problem. This one has to be a blue. One of these cells has to be red, because they can't be blue or purple. This one cannot be red or blue, so it must be purple. This one must be blue. And finally, we've got a blue-purple pair here, so again we can't have a blue-purple pair here. This one must be a red. This cell cannot be blue, red, or purple, so this one must be the 5. And this one must be the purple. Now let's look at these 5 diagonals. We'll put in 1s, 2s, 3s, and 4s around here. And let's look at these 4 corner boxes and ask where the 7s, 8s, and 9s can go in them. We know there's going to be 12 of them, 4 7s, 4 8s, and 4 9s. We could put 8 of them in these cells. We can also put at most 1 in these cells, because we've already used 2 here. We can put at most 1 in these cells, at most 1 in these cells, and at most 1 in these cells. That's at most 4 in these green cells. But we know there's 12, and we have 8 and at most 4, so in fact these must be 7s, 8s, or 9s, and we must have exactly 1 in each of these rows and columns. Now we can't have them here, because that would use up a row and column at the same time. So that would no longer allow us to get 4 different 7s, 8s, and 9s. In fact, these cells can't be 5s and 6s either. Because if this was a 5, we'd be forced to put a 5 in one of those. Can't put a 5 here, a 5 in one of those. Can't put a 5 here, a 5 in one of those, which breaks. And the same applies for 6s. So in fact, these cells are 1, 2, 3, or 4. And we get a little windmill pattern here. If one of these is a 5 or 6, one of these has to be a 5 or 6, one of these has to be a 5 or 6, one of these has to be a 5 or 6. So wherever the 5 goes, either they're always in the oranges or they're always in the greens, and the same applies to 6. And the same applies to the 7, 8, or 9 triple. Not necessarily the same digit, but if we have a 7, 8, or 9 here, we've used them up in this row, so there must be a 7, 8, or 9 here, must be a 7, 8, or 9 here, and must be a 7, 8, or 9 here. And we'll use that information in a minute. But for now, let's come back to these pairs here, 8, 9, 8, 9, 7, 9, and 7, 8. Wherever we put the 7 in this row, we're going to force an 8, 9 into one of these corners. Wherever the 8, 7 is, and we put a 9 in, we're going to force an 8, 7 into one of the corners. So in fact, these pairs here are the same 9, 8, 9, 8, 9, 7, and 8, 7 pairs. So let's ignore the rest of the grid and figure out where those two 7s go in these grey cells. Could we have, for example, 7s in adjacent corner boxes like this? And the answer is no, because the rest of the grey cells have to be 8 and 9. So if this was 8, this was 9, this was 8, this was 9, and this was 8. So these two are always the same number. So we can't put in 7, 8 and 7, 9. So in fact, the 7s are always going to go in opposite corners. But they can't go in opposite corner cells, because if we have 7 in both of these, and we put 8 and 9 to get our 7, 8 and 7, 9 pair, these cells also have to be 7s, because they'd see the 8 and 9. And we only have two 7s to place. Likewise, we can't put 7s in both the middle cells, because these would become 8 and 9, and we'd have to put more 7s in the corners. So the only place we can put the 7s is to have one in the corner cell and one in the opposite middle cell. And we're going to use that information a bit later. For now, let's get to this 9 diagonal. These cells cannot be 1 and 2, because that would break the 5 diagonal. And they also can't be 1 and 3, because that would break the 5 diagonal. So they add to at least 5. That means these ones add to at most 4 and have to be 1, 2, or 3. If they were both 1s, these would add to at most 7. So it can be 1, 2, 3, 4, 5, or 6. Can we have a 6 in one of these? And the answer is no. That would force 1s into the rest of the diagonal. But these 1s mean these would have to be 2 and 3 pairs, and these would have to be 2 and 3 pairs, which would force 2s and 3s into these cells, which isn't possible because we've only got one spare cell. Likewise, if this was a 6, we'd have 1s here, 2, 3, 2, 3, 2, 3, which doesn't work. So these cells can't be 6. Now we have a 1, 2, 3, 4, 5 quintuple. So the 5s are locked into these cells here, and now add to at least 6. So we can rule out the 3 from this diagonal. This 2, 6 pair gives us a 1 here. Can this one also be a 1? And the answer is no, because that would force this to be a 2 and 3 pair. And now there's no way to get a 9 along this diagonal. These add to 2, and these cells can't add to 7. So this cell must be a 2. These cells add to 6, and we have a 5 in them, so they are a 1, 5 pair, which rules out the 1, 4 pair from here. So in fact, this is a 3, and this is a 2. We have a 3 and 2 here, so this must be a 1, 4 pair. Oops. Now the same logic as before. If this was also a 1, 4 pair, then we'd have 1s and 4s in here. So this must be a 2 and 3 pair. This can't be a 2 and 3 pair, or we'd have 2s and 3s in here. So this must be a 1, 4 pair. Nice little logic going, cycling around the outside. Now this 1 resolves the 4 and the 1, which resolves the 5 and the 1, which resolves the 4 and the 1. Now we can remove 1 and 4 from here. We can remove 2 and 3 from here. We can remove 1 and 4 from here. And in fact, this cell has to be a 4. Now let's have a look at these orange cells again. This one is not 1, 2, 3, 4, 5, so it's 6, 7, 8, or 9. And our logic before told us if we have 5 and 6, then we have 5 and 6 in all the orange cells. Well, if we have 5 with a 7, 8, 9, then we have 5 with a 7, 8, 9 in all the orange cells. So either way, we know that these orange cells are always 5, 6, 7, 8, or 9. So let's have a look at this row. So 1 can't go in here, so it must go in here. In this column, we can't have a 2, 3 in here, so the 2 and 3 must go in here. We can't have a 1, 4 in here, so the 1, 4 goes here. And we can't have a 2 and 3 in here, so the 2, 3 goes here. Again, rotating around, getting these nice little pairs here. This 2, 6 pair, in fact, resolves the 3 and the 2 here. Now let's do a little Sudoku. We have 5s ruled out in these cells, so it must be here. 3 here, in fact, resolves this cage now. So we can put a 3 here. Let's get rid of that color. And these 3s seal these cells. So this one must be a 3. This one must be a 2. And these 3s force a 3 into this cell. And again, we'll come back to this orange cell. This can't be an 8 or 9. So it's either a 6 or a 7. And this is where the whole puzzle boils down to. Is it a 6 or is it a 7? And the answer is it can't be a 7. And to show that, we're going to use our little logic from before about the 7s in the grey cells. Supposing it was a 7, let's mark that as black. We know there is a 7 in a corner and a 7 in the opposite middle. It can't be these ones, because we've got a 7 here. It can't be these ones, because we've got a 7 here. And it can't be these ones, because we've got a 7 here. The only place those two 7s can go is here. And amazingly, this breaks the 50 diagonal. This cell is not an 8, 9, or a 7, so is at most 6. This cell sees these cells, which have become an 8, 9 pair. So this cell is at most 7. This cell here sees a 7, and also these cells, which have also become an 8, 9 pair. So this cell is at most a 6. We know that each of these orange pairs contains a 5 and a 7, 8, or 9. This must be the 7, 8, or 9. We have a 7, 8, 9 triple. This one is at most a 6. When we add up this diagonal, these are 3 different colors, so they add up to 7, 8, 9, 7, 7, 6, and 6 at most, which adds to 49. That is simply not possible. This cell must be a 6. In fact, all these orange cells are 5, 6 pairs. Now let's do a little more Sudoku. We have 4, 7, 8, 9 quadruple here. So these are 1s, 2s, and 6s. This one can't be a 1. This one can't be a 1. So in fact, this one is a 1. Now let's have a look at this cell. It sees a 1, it sees a 2, it sees a 3, it sees a 5, it sees a 6, and it sees these 3 cells. So in fact, this is a naked single 4. Sudoku on the 4s gives us a 4 here. And this 2, 6 pair means this one must be a 2 or 6. This cell here must be an 8 or 9, 7, 8, or 9, sorry. And this cell must be 2 or 6. And now we'll solve the whole rest of the puzzle by coloring. This cell here cannot be a purple or a blue, therefore it must be a red. This cell here cannot be a blue or a purple, so it must be a red. This cell here cannot be a red or a purple, so it must be a blue. This cell here cannot be a blue or a red, so it must be a purple. This one cannot be purple or red, it must be blue. Blue, red, must be purple. This one cannot be purple or blue, it must be red, which makes that one purple. One of these cells must be purple, and it can't be the bottom one, so this one must be purple. This one cannot be purple or red, it must be blue. That makes that one red. This one here, one of these cells must be purple, and it can't be this one, so this one must be purple. This one is not purple or blue, so it must be red. One of these has to be blue, and it can't be this one, so this one must be blue. One of these must be red, and it can't be this one, so this one must be red, which means this one must be purple. Okay, let me get rid of these greens as I don't need them anymore. And now we've done all the 7s, 8s, and 9 colouring except for one of these must be blue, one of these must be blue, and one of these must be blue. Now in this box, we've got 1, 2, 3, 4, 6, 7, 8, and 9, so this one must be a 5, which gives us the 6 and 5 here, which gives us the 2 and 6 here, which gives us the 3 and 2 here, and a 2 and 6 here. This cell here, the only white cell left, and it's not a 5 or a 6, so this one must be a 3. This one here must be a 1 or a 4, and we've got a 1 here, so in fact this one must be a 4, 1, 4. These 3 white cells must be 1, 2, 5, or 6. This one sees a 1 or a 2, which gives us a 5 and 6 pair. And this one sees a 1, so in fact this one is a 2, and this one is a 1, which resolves 6 and 2 here. These ones must be 4, 5, and 6, and we have a 4 and 5 here. So that one is a 6, that one's a 5, that one's a 4, that one is a 6. This 4 is finally resolved to this middle cage. That one is a 4, and we'll get rid of that colouring just to be safe. And now we need to look at this 50 diagonal again. We have a 7, 8, and 9 here, which are all different colours. And we have 2 different colours here. So they add to at least 7, 8, 7, 8, and 9. That adds to 39 at least. So these ones add to at most 11. But if this is a 6, that's a 5, and this is a 6, and that adds to 12. So this one must be a 5, this one must be a 6, and this one must be a 5. Now Sudoku on the 5s gives us a 5 in here. Sudoku on the 6s gives us a 6 here. 3 gives us a 3 here, and a 3 here. And I will get rid of these colours just to be safe. Now all we are left with are these 7s, 8s, and 9s. And in fact we have an 8, 9 pair here, so all of the blue cells must be 7. One last look at this diagonal. They add to 7, 7, 8, 9, 5 and 5, which add to 41. This one must be 9, this one must be 8. And that is my solution.